Okay, this is section 2.5, the chain rule. So let's preface this by going back and rethinking about the rules that we know so far. So we started off with doing the derivative by a limit definition of a derivative, which is a very tedious process, but it is where the derivative comes from. Then we started to learn some of the shortcuts, such as the power rule, which just says you bring the exponent down, reduce the exponent by 1, and that's the derivative of anything that you can write with a constant power. Constant meaning no variables in the exponents. Um, the next rules that we talked about were the product and quotient rules. So if you have a product of two functions or a quotient of two functions, there were rules to be able to take the derivatives of those. And then we talked about the trig derivatives, so the derivatives of the 6 trig functions, which kind of needed to incorporate the quotient rule in order to prove some of those, as well as some of the old limits, special limit properties that we knew. So now we are at the chain rule. And to understand the chain rule, really the main thing that you have to understand is that the chain rule is meant for composite functions. So you do have to understand what a composite function is. A composite function is when you've taken a function and evaluated it at another function. For example, we've actually been doing this. When we had to do the limit definition of a derivative, when we would do f of x plus h or a plus h or whatever, that's a composite function. Normally it would just be f of x, but we took the function x plus h and plugged it in to f. So that in itself is a composite function. That is composite. Because the outside function, or the main function, would have been f of x, and then the other function is x plus h, and then you would take x plus h and you would plug it in for x. So there is your composite. So the chain rule is a way to take a derivative of a composite function. So if we have y, which is a function of u, and we know that it's a differentiable function, and then we have u, which is a function of g of x, and it's also differentiable function of x, then if we take y to equal f of g of x, which is the composite function, and we know that that's a differentiable function as well, then this is the way we would write the derivative. So again, here's what you have to piece this together. So y is a function of u. U is a function of x. So if I want to find the derivative of y as a function of x, I can take all of this right here, which is u, and plug it in right there and get y as a function of x. So the derivative of that would be simply dy with respect to u. So I'm going to take the derivative of y, this one right here, with respect to u, multiplied by the derivative of u, that is a u on top there, multiplied by the derivative of u with respect to x. Or equivalently, because this is a way that you could see this, but you're probably going to see it written out in the way that I'm getting ready to show you here in the second part. If I want to take the derivative with respect to x of the composite function f of g of x, it is written f prime of g of x. So I'm literally taking the derivative of f, the composite piece stays on the inside, it stays the composite, times the derivative of the composite piece. A lot of people like to use outside and inside, so it's really the derivative of the outside function, keep the inside, and then times the derivative of the inside. So I'm going to spend a lot more time in the development of this early on, and then we're going to get into the examples because it's a lot to keep straight if you're just not thinking about it clearly. So another way you could think about this is that if I take y equals f of g of x, or f of u, then that is the same thing as when g of x is u. So it would be y prime in a different notation would be f prime of u times u prime. So again, from this notation right here, if I was taking the derivative of f of u, it's f prime of u, so the derivative of f first, keep the u inside, and then multiplied by the derivative of the inside of that thing, which is u. Okay, so let's go ahead and see how this works. Let's actually take a real function here and kind of see how it works. Now, in our case, in our example down here, y is the quantity of x squared plus 1 all cubed. And you wouldn't have to use the chain rule here. You could technically cube this whole thing, which means you could do x squared plus 1 times x squared plus 1 times x squared plus 1, and you could basically FOIL everything out and get a longer polynomial. You could do that and then just use the power rule. And that's completely up to you if you choose to do that. In this case, we're going to show how the chain rule works using this one because it's a slightly easier example. The chain rule is actually not specifically meant for this type of a problem. The chain rule is actually more meant for things where you cannot expand or simplify the function. But in our case, so let's talk about this one. So first of all, f of u. Well, f of u is going to basically be what would be the outside function. So if you can think about it, and I'm going to erase this in a second, to cover all this up, and just call what's inside there u. If that's all that it is, u cubed, the derivative, is going to be pretty easy to do. So we'll call it f of u cubed. Okay, but that makes u everything that was inside. So u itself is the x squared plus 1. So now again, hopefully you can see that if I wanted to, I would take the x squared plus 1 and I would plug it in there, and then we would get the actual function that y is above. That would be our f of u in this case. Whoops, didn't mean to erase the x squared plus 1. Let's put that back in there. There we go. Okay, so according to our definition above, it's going to be dy du. So I need to find that first. So dy du, or the derivative of y. Remember, f of something is the same as y. So you could call this y equals. So the derivative of y with respect to u, that's pretty simple. That is just 3u squared using the power rule. Then I have to take the derivative of du over dx, which is the derivative of the u function with respect to x. So that's just going to be 2x. So then dy over dx is the same thing as dy du times du dx. And yes, you should notice I'm not always saying over. For whatever reason in math, we've simplified this dy over du, and we just say dy du, which really is not very accurate to say. That's just the way it's kind of been said, because you think dy du, you think multiplication. I'm sorry, but you're just going to kind of have to get used to it. It's just the way it's been said. Properly, it should be dy over du. Just forgive me if I'm keep saying dy du. All right, so dy over du is 3u squared multiplied by du over dx, which is 2x. The main piece of this, though, is that u right there can't stay u. And the reason for that is I was looking for dy over dx. I am looking for the derivative of y with respect to x, meaning everything in the end should have the variable x in it. So when I go ahead and convert this, I basically just need to replace u with what we define u to be, which is x squared plus 1 in terms of x. So it's 3 times x squared plus 1 times 2x. Now, I'm going to scroll back up here, and I'm going to show you that this could have been done using that second method a little bit easier. If we look at that second method, this one right here, it just says take the derivative of the outside piece and then multiply it by the derivative of the inside piece. So if we kind of go back to this, it says take the derivative of the outside piece. So dy over dx. The derivative of the outside piece says bring the 3 down, keep the inside, but then reduce the power by 1. That's the derivative of the outside piece. It's what's outside that parentheses. Multiplied by the derivative of what's in the parentheses, or the composite piece, which is 2x. And then obviously the last step that I could do, because I didn't do this, I could clean this up a little bit. I can bring the 2x out to the front and multiply it. So you would just get 6x times x squared plus 1 squared. That's the most simplified form. All right, I know that was a long time on that very beginning part there, but again, I think it's important that you understand where this comes from. You must understand composite functions. So you have to be able to see when there is a function within another function. If you can decompose the function a little bit in your head, that's even better. All right, so now let's go ahead and take a look at the general power rule when it comes to this stuff. And you already know the general power rule for just a power function, but when it comes to composites, let's just make sure we see how this works. So this is the same basic example that we had. So y is going to be u of x all raised to the n power. Well, whatever it is inside there raised to the n power, the something raised to the n power is the outside piece. So I would treat it just like anything else. I would bring down the exponent, keep the inside, and then reduce the exponent by 1. But then the chain rule says I have to multiply it by the derivative of the inside piece, and the derivative of u of x in general is u prime of x. Okay, technically there's another piece of that, because then you would multiply it by the derivative of x, because x technically is composited inside of the u of x, but the derivative of x is 1, so we don't need to write that part. Okay, and just a shorter version of exactly what we just did. Instead of writing the u of x, maybe u is understood to be a function of x, and it's not explicitly written as that. So it would just be the same idea. Bring the n down, oops, reduce the n by 1, and then multiply it by the derivative of u. Okay, now let's go through some examples, because this is really going to be the best way for you to figure this out, is to actually just go through examples. And I know there's probably going to be some questions. I will try my best to answer those for you as we go. And hopefully I'll cover all the different things. If I don't, let me know, and I can certainly help you out. All right, so we clearly have a composite function, because in the first one with y, it's something inside of parentheses all raised to the third power, which means that it is something raised to the third power. The 3x minus 2x squared is the composited piece. So if I want to take the derivative, I take the derivative of the outside piece. So I bring the 3 out to the front, keep the inside the same, and then reduce the power by 1. But then I have to multiply that by the derivative of the inside piece, which is going to be 3 minus 4x. And notice that that derivative was a quantity, so I need to keep it in parentheses. Don't just write 3 minus 4x on the outside of the parentheses. It must be multiplied by the entire thing, so it needs to stay in parentheses there, since it was a quantity. Okay, so g of t. G of t looks like it's something that could use a quotient rule. In this case, we're actually not going to use the quotient rule, although you could. Either way you do it, you're still going to have a composited piece, because what you should see is the denominator there, 2t minus 3 is in the parentheses, all raised to the third power. That's a composite function. And just something else to let you know, and this is an important fact, anytime you have a fraction, the denominator is considered to be a composite. It is a composited piece. So whatever you have in the denominator is a composite function. We're going to rewrite g of t first. We're going to write it as -7, and then I'm going to bring the entire denominator up to the top and make it to a negative exponent. Okay, and that'll be easier to use for the chain rule now. So our chain rule says do the outside piece first. So bring the -3 out to the front and multiply it by -7, and we get 21. This is g prime of t. Keep the inside the same, and then reduce the power by 1. So remember, you're going from -3 down 1, so it's going to -4. And then don't forget to multiply it by the derivative of the inside in this case, which is 2. Okay, no reason to put that in parentheses because it's just 2. It's not a quantity. And if I'm saying quantity and you're not understanding, it means I've got things being added or subtracted together, not just products of multiplication or division. And then the only other things we could do is we can kind of clean this one up a little bit. We got 2 times 21, which is 42. And then the negative exponent can drop down to the denominator and make it a positive exponent. Did you have to do that step? No, but this just looks cleaner. All right, now we're really going to get into some challenging ones, because what I have next is I have a product rule, and inside of that product rule, we actually have a chain rule. Because what you should see is that 1 minus x squared, it's composited, it's inside of something, it's a quantity within some other function. So the 1 minus x squared is actually under the root. The root itself is an outside function. So first thing I want to do is I want to rewrite this. And you're going to find that you want to do this for a lot of time, especially when you've got roots. So it's x squared. Then I'm going to rewrite the root as a 1/2 power. So remember, square root is a 1/2 power. Now you should clearly be able to see that 1 minus x squared is a composite function within something to the 1/2. But the biggest thing here is, how do you recognize which rule do I use first? Well, the entire function itself is a product, which tells me I have to use the product rule in order to do this. That means you're going to start with the product rule. However, when you get to this second piece right here, when you get to the second function's derivative, that's when you apply the chain rule. So you'll have a chain rule within the product rule. So let's go ahead and see if we can work this one out. So we'll do the derivative of the first. So this is going to be f prime of x. The derivative of the first, which is 2x, times the second one. 1 minus x squared to the 1/2 power. Okay, we're still just doing the product rule. This was the derivative of the first. This is times the second, plus the derivative of the second. I'm going to leave a lot of room here. And then we'll do times the first. Times the first, that's the easy part. That's x squared. The derivative of the second piece. So now we're focusing on this one. This is where the chain rule comes in. Bring the 1/2 to the front. Keep the inside. Reduce the power by 1. So it's now negative 1/2. And then don't forget to multiply it by the derivative of the inside, which in this case is going to be negative 2x. And then we have times our first. Now that one can obviously be cleaned up a little bit. I can multiply the negative 2x times the 1/2, put the x squared on top, move the negative 1/2 exponent to the bottom. Not worrying about that in this case. I'd be very happy at this point if we understand how the whole thing worked with the product and the chain. All right, and then our last one on this page, the f of x, obviously this looks very much like a quotient rule. Could you make this a product rule? You absolutely could. You could change the x squared plus 4 in the denominator to x squared plus 4 to the 1/3 power, because that's what a cube root is, and then bring the whole thing up and make it a negative 1/3. We're going to practice doing this using the quotient just so that we can see how it works with a quotient as well. But you could change this one if you wanted to. All right, so let's go ahead and take the derivative, f prime of x, using the quotient rule. And again, the whole thing is a quotient, so that comes first. Within the quotient, you're going to use the chain rule. Quotient rule, derivative of the top is 1 times the denominator, x squared plus 4 to the 1/3 power, minus the derivative of the bottom. Here, let's actually rewrite this real quick. This was x over x squared plus 4 to the 1/3. So bring the 1/3 out to the front. Keep the inside. Reduce the exponent by 1, becomes the negative 2/3 power. Don't forget to multiply it by the derivative of the inside using the chain rule, which is 2x. And then after all that, times the top. All over the denominator squared. And again, that can definitely be cleaned up quite a bit. I'm going to skip that part for right now. If you want to, it'd be a good idea to practice the algebra there. I think we're going to go ahead and end this video right here. We will come back with a second one, maybe a third one. We'll have to see how it goes.